abelian category of coherent sheaves on some elliptic curve over a finite field, then associated to that is an algebra, an associative algebra called the Hall algebra of A, which already appeared in Jan's talk. So basically, the basis of this algebra will be given by isomorphism classes of objects, and the product is given by looking at all possible extensions of these two objects. But when you look at this abelian category, you sort of see that it's missing half. So because a vector bundle can have positive or negative degree, but only positive rank, there's kind of a nicer, more symmetric object, which is the Z mod 2 graded derived category of A. And similarly, the Hall algebra of that A kind of naturally it wants to be doubled. So we really want to take something like the Hall algebra of this category. And well, it was kind of a mystery for a while of exactly how to do that, but there's a substitute. So you can take the Drinfeld double of this Hall algebra of A, and it's a very nice object, kind of connected to various subjects. So double affine Hecke algebras, whatever they are, skein algebras of the thickened torus, which is where my interest in these Hall algebras came from. But the problem is, yeah, how do you go directly? How do you construct this naturally from the Z mod 2 periodic category? Yeah, so I want to explain how you can do that. So that would, for example, then tell you all this has much more symmetries than this abelian category. And if you had a natural construction, you would immediately know that all these symmetries also act on this Hall algebra. So, and in fact, I'm only going to use, so this is a very specific example. I'm only going to use the fact that this category here is old Calabi-Yau. So where my own interest comes from is in defining Hall algebras of Fukaya categories. And there you don't have a priori in an abelian category, you just have a triangulated category. And so you want to define some kind of Hall algebra. Okay, so if we replace this Z mod 2 here by Z graded, usual derived category, then we already know how to do this. Construction of the Hall algebra. This was solved by Bertrand Thoen several years ago by now. And a key ingredient in his construction is something called the homotopy cardinality. That's kind of the starting point. So well, if C is, let's say, X is some homotopy type, and it should be somehow very finite in that the homotopy groups are all finite and eventually trivial for I big enough. So for example, classifying space of a finite group. And then there's a natural way in which you count kind of the, well, of course you could take the number of components of the homotopy type, cardinality of pi 0, but there's actually a more complicated thing that turns out to be easier to compute, or kind of better behaved, which is this homotopy cardinality of X, which is where you take a weighted sum over connected components, and then you take an alternating product over the sizes of the homotopy groups. Pi ix with respect to that base point. Yeah, so it's divide by size of pi 1, multiply by size of pi 2, and then so on. And it's not really an infinite product because of my conditions. So yeah, this was somehow, this notion is by nowadays there's a more sophisticated version of looking at it. It's kind of absorbed in this formalism of ambidexterity and norm maps that Hopkins-Lurie developed. But for us, we're going to stay with this kind of just writing down a formula. And so I'm not an algebraic topologist, but I do look at DG categories. So if C is some DG category, and let's make it over a finite field so that we eventually have these finiteness conditions, then you could extract a homotopy type from that, which is just the space of isomorphism classes of objects. So C tilde, also sometimes called the core, this is the space of isoclasses in C. So technically, if you want to kind of actually write it down, what you do is you take the DG nerve of C, which is this spatial set, which you can think of as an infinity 1 category, and then you take the maximal Kahn complex inside that, meaning the kind of infinity groupoid, and that's this space here. But I'm not really going to care about the space itself, but just we only need to know what its homotopy groups are. And pi 1 of this space is the automorphisms of an object, and the higher homotopy groups of this space are the negative X groups from objects to themselves in this category C. So that means, well, we could write down now, assuming this is finite enough, there's a finite number of isomorphism classes, and X groups eventually vanish, then we can consider the homotopy cardinality of this space of objects. And so it's given by a sum over isomorphism classes in C. And yeah, I want to introduce some notation maybe before I write that down. So we assume that the X groups are all finite dimensional, and 0 for I very large or very negative. And then the following thing makes sense, so a kind of Euler pairing, but
you need only in one direction.
Yes, so for this I only need negative, but for the notation I want to introduce, I need both. Yeah, so I want to consider in general a kind of part of the Euler pairing. So there's an Euler pairing, which we just heard in Tom's talk, which would be the sum over all integers minus 1 to the I dimension of xi. But now, more generally, I want to just go over some subset of the integers and consider a kind of truncated Euler pairing. So this will then depend on the actual isomorphism classes and not just the classes in the Grothendieck group. Yes, and so then this becomes q to the minus pairing, where I take sum of dimension of the negative X groups and divide by size of automorphisms of X. And as Maxime indeed pointed out, for this to make sense, I need the negative X groups to eventually vanish.
Is this an infinite sum?
Yeah, sum is not convergent, but it's numbers.
No, I'm assuming I have finitely many.
Oh.
But you have coherent shifts on E?
Yeah, this is not an example that will work.
Finitely many. It's not realistic.
Yeah, that will be. I will fix that. I agree that's not very realistic. I want to first explain kind of the basic idea, and then we'll do a relative version of that, and that will be a more realistic assumption. But the idea is most clear in kind of this toy example, maybe. So I'm assuming finitely many isomorphism classes.
But it's not triangulated category yet.
No, it's not triangulated. Yeah, I mean there are some like augmentation, I don't know, category of rank 1 local systems on a surface or something. Yeah. So, but there are not very many natural examples. But I will fix that. But now the point is, you can kind of notice that instead of requiring all this finiteness, you can somehow, if you assume that the category is Calabi-Yau, then the sum over negative dimensions of negative x groups will be more or less the sum of dimension of the positive x groups. So if you impose more symmetry, then you find that you can actually get away with less finiteness. So assume C is n Calabi-Yau for even n. Then, yeah, so Calabi-Yau means this, what we have just also in Tom's talk, that there should be this duality for these x groups. So then you can rewrite this term is 1/2 the Euler pairing minus a kind of small correction term if I take the sum of alternating sum of sizes of x groups from 0 to n. And yeah, that n was even was important here, so I get a formula like this. Yeah, this term here, so this is an n. This term here definitely makes sense even if the category satisfies less finiteness. So I'm going to say that C is degree-wise finite. Means just that the dimensions of the x groups, they're all finite, which I definitely need to make sense of it being Calabi-Yau or right Calabi-Yau. But they could go on forever in both directions for positive and negative I and could be not periodic. But for example, a Z mod 2 graded category or Z mod 2 periodic category will satisfy this condition, but not this stronger condition that it's eventually 0 for I big enough.
Is this Calabi-Yau compact assumed or after?
It's an abstract category.
No. But in abstract sense, there is no proper.
Yeah, so it's not proper. It's not locally proper.
So I don't understand. So what is x bracket x in this case if there is infinite?
Yeah, that's a good point. So this guy here now makes sense. So this makes sense for degree-wise finite C. This guy here doesn't make sense. So we're going to do we're just going to forget about it. So it turns out that this is somehow the more important term because it really depends on the isomorphism class of x, whereas this term only depends on the K-theory class of x. So when you remove this, you're kind of doing some kind of twisting, so people who know about Hall algebras, when you construct a Hall algebra, you actually do this twisting of the multiplication by the Euler pairing. And forgetting this term means you automatically get the twisted thing to begin with, which is more natural. So for experts on Hall algebras, this has kind of some very nice effect. Yeah, but I'm going to just pretend it doesn't exist, kind of to derive my formula. So yeah, as was pointed out, there's somehow, I don't know so many interesting examples of even Calabi-Yau categories with finitely many objects that kind of naturally appear. So to get more mileage out of this idea, one goes to a relative version. And so we'll be talking about not categories which are Calabi-Yau, but functors which are Calabi-Yau. So CY structures on functors. This originally was kind of proposed by, again, Bertrand Tohen, and then developed by Brav Dickerhoff. For me, it's always going to be what they call weak right Calabi-Yau structures, for those who know what that means. What's the basic idea? So Calabi-Yau category, a motivating example would be category of local systems on some compact-oriented manifold, and then Poincare duality tells you that you have this duality, Calabi-Yau duality of the category. So the motivating example here is if you look at the functor, you have a compact-oriented manifold with boundary, then you get a functor from local systems on M to local systems on the boundary. This is now a Calabi-Yau category. And Poincare duality doesn't hold on M, but you have instead this long exact sequence which relates the cohomology of M and its boundary. And that you take that long exact sequence as kind of the essential property that a abstract functor between DG categories should satisfy for it to be Calabi-Yau. So a functor f from B to A, so a functor of DG categories, then, well, I'm not going to tell you exactly what Calabi-Yau structure means, but the important consequence is that you get this long exact sequence. Take x in B from x to y, maps by f to x I, f of x inside A, f of x to f of y. Now this guy here, because A is, yeah, there's some dimension here. A functor is n Calabi-Yau. And it means, so n is like the dimension of this M over here. It will mean A is n minus 1 Calabi-Yau. So this here will be dual to x n minus 1 minus I. And then I can use the dual of the functor f to go to x n minus 1 minus I inside B from y to x dual. Okay, and I could, so whatever a Calabi-Yau structure, and then kind of course, instead of having long exact sequences, we should have some kind of fiber sequence in a correct homotopical sense, and that's how you define Calabi-Yau functors. So if I have one of those guys, so suppose f, this is NCY functor, and now n should be even.
Sorry, what's the definition? I can't quite understand the definition. Is n
The definition is something that tells you have this long exact sequence. To say it correctly, you say that this is really a bimodule over B cross B, and you want a triangle in the category of B tends to B of bimodules. That is exactly this. That's a weak right Calabi-Yau.
The next term is xi plus 1 of x.
It then continues xi plus 1, yes.
So does this imply that the target is n minus 1 Calabi-Yau?
Yeah, so the way I define it, I want the part of the data is an n minus 1 Calabi-Yau structure in A plus then something that a coherent square that gives you this long exact sequence. I think maybe there's some version of definition where you don't automatically assume that this is Calabi-Yau, but yeah, I'll want that.
And the symmetry or anti-symmetry of the cup product in the usual duality, is it incorporated in those type of definitions?
So there's a stronger condition where you have cyclic invariance somehow of this. I only want that you have morphisms of bimodules. That will be enough for me. Okay, so yeah, so one of these Calabi-Yau functors, n should be now even. It's over maybe finite field. And I'll also need that the induced map now on isomorphism classes, so pi 0 of f is the induced map on isomorphism classes, has finite fibers. And then I can write down a formula In fact, I'll write down a functor. So first I want L. So L of f will be some linear function from the vector space of complex linear combinations of isomorphism classes of C, just down to C. It's a linear functional. And how is it defined on a basis element y? Take a sum over isomorphism classes in B, which map to y. And here you take size of automorphisms of y, square root, divided by size of automorphisms of x. And then there's an important power of q to the 1/2 some integer gamma f comma x.
Fabian, I think you lost in the notation. What is fn? F to the power n or whatever. P0 or what?
F tilde.
F tilde.
Oh, it means f tilde is a space of objects. So you want maybe this is the induced map on sets of isomorphism classes.
So what is the exponent of q1 of?
Yeah, so I'm going to write down what is gamma.
What is C?
C is complex numbers. Or the other is the curly is a category, DG category.
Which one? I mean, is B and A? That's not related.
No, it's C. What?
Oh, sorry. Yeah. You're right. Yeah, this should be A.
It's a little bit better. What is the exponent for Q?
Yeah, I'm going to tell you now. So gamma of f comma x is basically some dimensions of sizes of x groups. So it's the alternating sum of dimension of x group from 0 now to n minus 1 plus rank of the connecting map in this long exact sequence from x to n, x comma x dual to x0, x comma x. So it looks like it depends kind of on the Calabi-Yau structure, but if you know you can compute the rank of this connecting map kind of a priori just if you know f. So
LF should go from isoclasses of B, not E.
No, isoclasses of A. Yeah. So how you should think of it is in the setting where all my x groups kind of eventually vanish for negative enough I. What I can do is I can pull back functions from A to B via f, and then I can just sum them up over all isomorphism classes of B and sum them in the sense of homotopy cardinality, so with the correct weight. And what you find is you can rewrite that formula in the correct basis in some way, just like I did with in the absolute case. If I just have an even Calabi-Yau category, you can rewrite, you get some terms, and you can rewrite them given Calabi-Yau duality in some way, which makes sense more generally in for these degree-wise finite categories. So you derive it kind of just kind of repeat what I did the absolute case, but right. So if you put if here the special case where a is 0, then it's really just you rewriting this, but the exponent instead of being the sum over negative x groups becomes this term here.
So and the example of local systems of a manifold in the boundary will go.
Yeah. That would be an example. But then it's kind of not really infinite. So
You do not assume that A is Calabi-Yau.
No, B is Calabi-Yau.
A is Calabi-Yau, B is relative
You
Calabi-Yau.
assume that A is Calabi-Yau.
Yeah, but if A is 0, then then relative Calabi-Yau just says that B is Calabi-Yau. Yeah. Okay, so I want to write down. So I've explained how you can arrive at this formula, which I'm just kind of dropping here. You can derive it by kind of rewriting what is pullback of functions and then correctly integrate in this homotopy cardinality counting measure. But I want to give another analogy, which I hope doesn't get me into trouble. So DG category, namely analogy with something that happens in supergeometry. So DG category A with an odd Calabi-Yau structure. I want to think of as, in this analogy, as over here, a superspace M with odd symplectic structure. And I want to think of, for me, this is somehow like the non-commutative geometry, what I learned from Maxime, to view these, with apologies to Denis, to view these DG categories as some kind of non-commutative spaces, and this is the commutative world, or super commutative world. So that's A. What's my functor F? So F is a relative Calabi-Yau functor, is even Calabi-Yau, even relative Calabi-Yau. In this analogy, becomes a Lagrangian submanifold inside this odd symplectic superspace. This set of functions on isomorphism classes corresponds over here to space of half densities on M. And the half densities kind of in the formula corresponds to the fact that I have lots of square roots in my formula. And then this functional, which I'm defining on this vector space, corresponds to integrating. So there's an invariant way to integrate a half density over a Lagrangian L. Basically, because if you have Lagrangian inside odd symplectic thing, then the determinant bundle of the tangent space to the Lagrangian provides a square root of the determinant bundle of M itself, the tangent space of M. So if you can pull back a half density on M to a one density on L, and then you can invariantly integrate that.
What's an odd symplectic structure? That the pairing goes to an odd space, or that the dimension is?
Yeah, so kind of conjugate coordinates will be in different parity. Yeah.
Sorry, I missed it. What's L of A?
L of A was just a space of. I didn't define it. Yeah, this here. L of A will be just a space of complex linear combinations of isomorphism classes on A. Finite, yeah. Finitely supported functions on. But so when you define when you do pullback, or I don't know, when you define Hall algebras, you somehow have to decide, do I want to think of these guys as functions or measures on the set of isomorphism classes? And the change of bases which interpolates between the two is multiplying by this homotopy cardinality. And what you find is that the formula only makes sense in the bases where you just write in between functions and measures. So you're sort of dealing with half densities. But that might be a bit cryptic comment. I'm not sure I want to say much more. But
So does it perform for Z2 graded?
No.
I think it's general. It should work for Z graded as well. Because you impose this condition.
well, Z graded is more special than Z mod 2 graded. Okay, so somehow the reason why you can invariantly integrate half densities on this kind of guy is the same reason that this formula is a sensible thing to do in this world. And there's a connection. So when you have these kind of, when you have a Calabi-Yau category, the space of objects is a shifted symplectic manifold or space. And then if you have a relative Calabi-Yau functor and you look at moduli spaces of objects of these categories, it is kind of Lagrangian map to some shifted symplectic thing. So there's a, this is a good analogy, but it's still a bit mysterious to me what it actually means. Okay, so I wrote down some formula. I haven't given you any theorem yet. I've just given you a definition. So what's the theorem? Yeah, the theorem is about kind of Lagrangian correspondences. So Lagrangian submanifolds in a product of two things. So what's an n Calabi-Yau span? Well, it's some kind of diagram where you have B DG category mapping to DG categories A1 and F2, A1 and A2. And the kind of total functor, so F functor from B to the product is n Calabi-Yau functor. So instead of a manifold with boundary, just a kind of Bordism manifold with boundary decomposed into two pieces. And now, well, we get a linear map from kind of isomorphism classes on this product. And because this space has a natural inner product, which is just the naive one, where the natural basis is just the orthonormal basis, we can turn this linear functional into a linear map. So we get a linear map, L of f, from this vector space of isomorphism classes on A1 to L of A2. Well, and supposing the induced, so this functor over here, F1, has to have finite, has to have finite fibers on the set of isomorphism classes. So pi 0 of F1 tilde from iso A1 to iso B has finite fibers. Then you get a well-defined map like this.
Yeah. So you're interested in your A, B, even Calabi-Yau, and you will count something for odd Calabi-Yau.
So I'm kind of counting objects in this even Calabi-Yau category, but
which one is even?
B is even.
B is even.
So a functor being n Calabi-Yau means that the target is odd Calabi-Yau. So this here is
the local system on surface.
It's yeah, like on a local system on even dimensional manifold with boundary.
Okay.
So this will be n minus 1 Calabi-Yau. Okay. Yeah, so now why am I saying this thing for spans? Well, now with spans, you can compose them, like composing Lagrangian correspondences, which means that if you have one of these spans, so these are all DG categories, and then you take the fiber product over here, and you get some, yeah, so just like you compose spans, but the definition depends on knowing what the homotopy fiber product of DG categories is.
So did you explain the definition of ISO of the map induced on from LA1 to
LA2? Just induced map on set of isomorphism classes.
Is it from B to A1?
Oh, sorry. That's correct. B to A1. Thank you. So just a map induced by
No, the map from LA1 to LA2. Did you explain or no?
I don't have any conditions on it.
No, but how do you define it? Do you use this formula to integrate down one of the fibers or something like this? How do you define L of f?
Well, my formula tells me if I have a functional on, it doesn't give me a linear map like this, but it gives me a linear map on the tensor product of the two spaces, 2 down to C. And using the inner product on here, I can turn it into a linear map.
The inner product given by the...
Just a standard inner product where the isomorphism classes form an orthonormal basis.
Ah, that's
Yeah.
the inner product.
Okay, so then theorem which is in this joint work. I'm talking about is L is a functor.
Okay, categories are not closed on the extensions. It's that, yeah. These categories are not triangulated.
No, they could be triangulated.
Not necessary.
Because I'm only demanding now that pi 0.
Yeah, okay.
So an example will be if you have here triangles in some category and you map it to 2 copies of that, right? So like when you define. Yeah. So now there are actual examples where all these are triangulated and they still satisfy my finiteness conditions. Okay, and somehow the proof, it's not, I mean, extremely long, but because I defined this thing using some formula, it's some kind of computation to check it's actually a functor, not somehow extremely conceptual. Yeah, but it means, right, so I have these 2 spans. I can either get a linear map from this linear combinations of isomorphism classes over here to here, and then from here to here, or I can use this span. So, okay, and it's a functor from where to where, right? So it's from some category of n Calabi-Yau spans of DG categories satisfying this finiteness condition to vector spaces over C. And it also looks like there's there's like a higher categorical generalization where you don't, instead of considering 1 spans, you could consider k spans, and then you map to have some higher category here of k vector spaces. But we don't develop that in this paper except for 2 spans which we need for an application to Legendrian.
But to compose correspondences, you need to have some fiber product, and this should be taken in the homotopy theoreticals.
Yeah, so this is naturally a like higher category, but for us it's enough to consider it as it's a homotopy category. So to consider it as an ordinary category, because you have a functor to an ordinary category. So you can immediately here just pass to the homotopy category of the higher category of spans. But composition should be defined in this homotopically correct way. So morphisms here are really more like equivalence classes of spans, 1 spans, up to equivalence of this B. Okay, so the first application of this theorem so you can now look at, well, where's this notion of homotopy cardinality used? Previously in mathematics, and I said that one use of it was in Towen's definition of derived Hall algebra. So now we have this kind of variant now of homotopy cardinality where we assume more symmetry, we assume Calabi-Yau, but we assume less finiteness, and we can sort of do an analog or a variant of that under these different conditions. So application is, well, to solve this problem which I told you in the very beginning, and more generally to define Hall algebras in many new cases where it was previously not clear how to define them. So C will be a degree-wise finite, meaning that the dimension of all the X groups are finite, odd Calabi-Yau. And over a finite field and triangulated, or pre-triangulated. Not necessarily periodic. Yeah. For example, 2 periodic would be fine. But there's interesting examples of, for example, these cluster categories. If you take a Calabi-Yau 3 category of some Ginzburg DG algebra and you take a quotient by, well, in that case it's an even Calabi-Yau, but yeah, so there's categories which appear also naturally where the xi groups go on forever for both positive and negative I, and they are Calabi-Yau, but they're not periodic. And everything we do somehow works just as well under those weaker assumptions. Yeah, so to use my formula, I need some relative Calabi-Yau functor. And that is the following. So in fact, better to view it as a span. So I can look at the category of triangles in my category C. So I'm going to write that as C to the A2. It's like functors from the A2 quiver to my category. So this is the category of triangles. And I can, if I have a triangle X, Y, Z, I can send it to the 3 objects X, Y, Z. And one leg is going to be sending it to the pair Z, X. And then another functor will send it to the extension. So this sends this thing to Y. And this functor is now relative even Calabi-Yau of dimension 1 more than whatever my C was. Okay, right. So in the formula, I needed this to be an even Calabi-Yau functor. That's why I need C to be an odd Calabi-Yau triangulated category. And this, because kind of if I take a pair, and because of I'm assuming my category is somehow very finite, it satisfies this condition that there's finitely many isomorphism classes of triangles for a given X and Z. So I get a map, kind of a product from L of C, tensor L of C, to L of C, other C. And of course, you want to know it's associative to get an actual algebra, and associativity follows exactly by this theorem here of functoriality. So this is associative. This theorem, the only one I told you so far, by kind of a general formal argument that people in Hall algebras know. This is associative. It's also unital because the 0 object gives you a unit. So it's something that you would call the Hall algebra. So Jan also talked about there's some kind of more sophisticated version. You could upgrade this to motivic. Then you would just need to require that your objects in your category form some constructible stack. And then you could presumably do all this kind of a motivic version of this Hall algebra, where this number Q over here is replaced by a motive of affine line. And then also Davide told us about these. They appear, the cohomological Hall algebras appeared in his talk. So I'm not sure if, I haven't thought about trying to do those in this setting, but maybe that's also possible. And so my co-author on this paper, Misha, is really an expert on these Hall algebras, and it was very wonderful that, so he was able to show that there's all these existing constructions of Hall algebras which somehow make some choice. So they start with some abelian category or some exact category or some localization, and then produce in the end some Hall algebra. And he was able to show kind of whenever both things are defined, whenever this Hall algebra is defined and the other one, which you construct by some kind of less natural way than the two agree, of course, because there is only one Hall algebra in some sense. Yeah, so in particular, like this example where you take the Ringel Hall algebra of an abelian category and then you take a Drinfeld double, agrees with this definition of Hall algebra.
Yeah, but here you don't need triangulate category, you need full subcategory to close under extensions. It's like sectors and for region stability. Yeah.
Extension closed.
There is also this framework of Kapranas-Bickerhoff for all whole algebras to see that space.
Yeah, these spans here are part of kind of the first step in this two-sequel space. And then you need some kind of way to go from the abstract span to actual vector spaces. Right? And we're providing a new functor which helps you do that. So you can see it as another way to go from the most abstract version of Hall algebra is just saying that the product is this correspondence. But if you want to work with something more concrete, some actual algebra, then you need some sort of functor to apply to this. And well, we're defining this functor in this setting. Okay, so let me tell you about a second application. By the way, I haven't told you what if you use this definition, you get some complicated formula, which is not super useful, and then we simplify. We kind of say more explicitly in terms of the X group inside the actual category C and not the category of triangles. You can write down what's the formula for this product. Okay, so a second application.
And for higher genus terms, you also get the same answer as
well, they're not Calabi-Yau. Yeah, but I can take a Fukaya category of a higher genus curve. And I would get some kind of Hall algebra of that. But
yeah, but also it's analog of like usual what's called people two Calabi categories. Even not odd, yeah. You consider maybe I don't know some Calabi-Yau some maybe even dimension, and consider actual algebraic variety and closed subset. And they consider quotient perfect complexes in the formal neighborhood, but complexes supported on the subset. In case of three Calabi-Yau, it's what is two Calabi-Yau categories which with infinite non-priori construct. Yeah, it could be one of examples of such. Yeah.
But here we need to start with something old Calabi-Yau.
Yeah. So we start now maybe with even dimensional Calabi-Yau. I consider
like higher cluster theory. They consider also cluster categories which are old Calabi-Yau, and then you could apply to this.
Yeah, and you get this finiteness automatically.
Yeah. Okay, so if you look, there's a second place in mathematics where this homotopy cardinality has appeared that I know of, which is in Legendrian knot theory. So second application will be to Legendrian knots. So, well, I'm going to consider some Legendrian knot or link in standard R3, the standard context structure. Then you want to enhance it a little bit by some kind of grading structure like you do for objects in the Fukaya category. So you can talk about Z to M or C mod M gradings. Which means the kind of the total winding number. To have this kind of structure, I need the total winding number along some component of L to be divisible by 2m. In particular, if m is 1, Z2 grading is just an orientation of L. So if you don't...
So L is a link, not so
could be a link, yeah, it doesn't really matter for me too much. In fact, also we look at tangles in the paper, and you can do everything for tangles as well. Yeah, and now there's, well, one of the problems in Legendrian knot theory was to distinguish Legendrian knots which are the same as topological knots. So there's an isotopy through kind of just topological knots. But maybe there's no isotopy through Legendrian knots. So they're different really as Legendrian knots. And there's some invariants which were developed to show this. So to L, one basic invariant is a kind of knot polynomial. So which is called the ruling polynomial. P sub L. So it's a Laurent polynomial with non-negative integer coefficients. And these kind of, by one definition, they already have a combinatorial interpretation for what those coefficients are. Ruling polynomial. So yeah, if
it's Legendrian invariant, yeah.
Yeah, it's an invariant of a Legendrian knot, and it depends also on this choice of grading group. So there's a Z mod 2 graded ruling polynomial, a Z mod 4 graded, in fact also odd, but also Z graded ruling polynomial. And on the other hand, yeah, also if m is equal to 1, so the Z mod 2 graded ruling polynomial is in fact not a Legendrian invariant, but it's just a topological invariant, and it's part of the HOMFLY polynomial of that knot. So the kind of leading part in the A variable of the HOMFLY polynomial. On the other hand, there's a kind of more sophisticated invariant, which is the augmentation category of L. And then there's some variants. I'm going to use what's called aug plus of L. And kind of morally, so to L, well, to L, there's something called the Chekhanov-Eliashberg algebra, DG algebra, which you can define combinatorially in terms of the projection of that knot to R2. It counts some kind of disks. And generators are given by self-intersections of the projection. Then to understand this Chekhanov-Eliashberg DGA, you look at augmentations of it. And these actually form objects in some category. So this is an A infinity category. Defined over integers. In particular, you can define it over a finite field.
But do you remember correctly, it's actually free finitely generated algebra and differential quick generations. Find the expression in the previous one. There's certain Z gradients which you can't control.
What do you mean?
Oh, no, there's Chekhanov-Eliashberg algebra. It's essentially free finitely generated algebra.
Yeah, it looks like causal dual to something.
Yeah. Not causal dual, because differential gets 1, you get.
It's causal dual to some curved infinity algebra.
Yeah, curved.
Yes.
Yeah. Okay.
Yeah, you can view these objects in here as Marcaton elements in that curve. Yeah. But, yeah.
It's smooth kind of finite type. Yeah.
It's Z mod 2m graded. And will be locally proper, degree-wise finite. Yeah, so it's not quite even Calabi-Yau. So it's almost, it looks sort of like category of local systems on a surface with boundary, in the sense that it has a functor to category of rank 1 local systems on just the underlying curve of that link. And this functor is to Calabi-Yau. But
it can define not only rank 1 if you consider.
Yeah, you can. Yeah. But then I'm not finite. So, yeah. To compare with the ruling polynomial, I restrict to things which are rank 1 here. Okay, yeah. But you could, of course, generalize to higher rank. Okay, so this functor, and yeah, but this is kind of some very small correction to this being an actual Calabi-Yau category. So you can almost think of this as a 2 Calabi-Yau category, because the correction just comes from cohomology of S1, or several copies of S1, which is usually a small term in this long exact sequence. Okay, so I can.
So if I replace R3 by a contact sphere and the boundary of the tangent bundle and look for similar functor from higher category.
Yeah, so in general, if L is in some bigger contact manifold, this is not a relative Calabi-Yau functor unless L is a zero object in Fukaya category of the symplectization of that contact manifold. So in general, you have a Calabi-Yau functor to local systems times Calabi-Yau of the symplectization of your ambient space. Yeah, so here it's zero object in Fukaya of R4. Okay, so what was proven previously by Ng-Rutherford-Shende-Sivek was that if you take the homotopy cardinality of this if your gradient group is Z, so M is 0, then the homotopy cardinality of this as a category over FQ will be essentially this ruling polynomial where you set Z equal to square root of Q plus 1 over square root of Q. And then they had a conjecture that there should be something also if it's periodically graded, and we can prove that conjecture.
But with this PL, should this sort of have an element of the scaling algebra?
It's just a polynomial, Laurent polynomial. Yeah, in general, you want to think of it. The way you generalize not polynomials is to view them as elements in some scheme module. Yes. So the theorem we prove is that take this Z mod 2m gradient ruling polynomial. So in the case m equal 1, it's part of the HOMFLY polynomial of q1/2 minus q to the minus 1/2, where q is the number of elements in my finite field. It will be equal to, well, what I defined over here, L of f of kind of constant function 1 on set of local systems of rank 1. So call this f, which is more explicitly, so it's some, yeah, I mean, the explicit formula is that formula. Where now I guess you go from 0 to 1 because n is 2, and then you have this term which comes from the rank. So it depends a little bit on this functor f, and if it's a knot, it has only one component, then you can forget about this functor, and it's something that depends only on aug plus of L. So it provides some kind of intrinsic, what you see is that you can recover this not polynomial intrinsically from the augmentation category. So if there's several ways in which you can define this augmentation category, also with microlocal sheaves, for instance, and then this theorem tells you a priori that you can read off kind of this not polynomial from whatever definition of this augmentation category you use. So this was previously a conjecture of Ng-Rutherford-Shende-Sivek from about 10 years ago. I don't know if anybody tried to solve it, but yeah, that kind of gap is now closed. Yeah, and you could potentially, right, if you have now, well, you need to go 2 dimensions up to have the correct parity, but if you had a Legendrian, not but threefold, you could define some kind of invariant of it, which I don't know if if there's any kind of not polynomial interpretation. But yeah, we would have now some way of defining invariants in this periodic setting whenever you have a relative Calabi-Yau functor. Okay, so thank you very much. Let me stop here.
Comments. How people define this ruling polynomial?
Well, one way to define it is just using some kind of skein relation. But there's a combinatorial interpretation where you look at the front projection of the knot, and then you count some kind of regions, which So it already has some combinatorial interpretation, and now it has an interpretation as a kind of homotopy cardinality of a category.
Let me ask you a question. Is there a B-side of this story?
Of this not polynomial? Yeah, it's I don't know. It's a good question. Consider something like some kind of torsion sheaves on affine plane. They objects in some 2 Calabi-Yau category. So if you fix, yeah, I'm not sure. So what a good question would be kind of maybe can these categories appear on the B side somehow? Probably, but I don't know how to do that.
But I just really want to congratulate you because it was a dream for 20, 30 years to move in topological field theory to arbitrary dimension. And
Thank you very much.
Other comments or congratulations?
Well, if not, thanks again.